Good day. Thank you for being here today. So I am here to talk to you about Self-Similarity and Mandelbrot Set. A fractal is a geometric object that is similar to itself on all scales. If you zoom in on a fractal object, it will look similar or exactly like the original shape. This property is called self-similarity. An example of self-similar object is Sierpinski triangle shows in the screen. As one looks closer, we observe that the large triangle is composed of three smaller triangles half the size of the original, which in turn are composed of three smaller triangles, and so on and so on. On all scales, the Sierpinski triangle is an exactly self-similar object. The property of self-similarity or scaling is closely related to the notion of dimension. In fact, the name fractal comes from the property that fractal objects have fractional dimension. The concept of self-similarity naturally leads to the generalization to fractional dimension. If one divides a self-similar D, which is the dimensional object, into n, which is the smaller copies of itself, each copy will be scaled down by a factor r, where r is equals to 1 over n to the 1 over d. Now, given a self-similar object of n, part is scaled down by the factor r, we can compute its fractal dimension, which is also called similarity dimension from the above equation, as d is equals to log n all over log 1 over r. As an example, let us compute dimension of famous curve of von Koch, which is sometimes referred to as Koch snowflakes. The Koch snowflake is generated by a simple recursive geometric procedure. Number 1. Divide a line segment into 3 equal parts. 2. Remove the middle segment, which is equal to 1/3 of the original line segment. Number 3. Replace the middle segment with 2 segments of the same length, which is equal to 1/3 of the original line segment, such that they all connect. For example, 3 connecting segments of length 1/3 becomes 4 connecting segments of length 1/3. To complete the shape, the above procedure is repeated indefinitely on each line segment on the side of a triangle. Images showing the procedure and complete Koch snowflake are shown below. Two figures are said to be similar if one is a scaled up or a scaled down version of the other. In other words, similarity allows us to use not only rigid motions but also expansions and contractions. Similar figures have the same shape but may be of different sizes. We say that a figure has exact self-similarity if it is composed of several pieces. Each of these is similar to the entire figure. In this example, we see that a solid square is composed of 4 smaller solid squares. It is self-similar. Or simply that an object is self-similar if one part can be enlarged or shrunk to create the original object with an iterative process. Iterative process means to repeat process over and over again. Some examples of self-similarity are fractals, which I said earlier, and the Cantor set. Now, let's move on to Mandelbrot set. But before that, here is the video showing who discovered this wonderful creation from the world of mathematics.
The fractal stuff, what was the origins of that?
January 44 that I discovered that I had a gift for math. I started studying well above the level in which I would have been. And then suddenly the professor asked a question. Nobody had a clue. And for me it was completely obvious. So I lift my hand and say, well, I think the answer is very simple. That, and that, and that's it. The prof did not know this answer. His answer was very much more complicated. And then it was like I don't know, a curtain opening. So I saw that well, my gift to mathematics was different. I discovered this immense, amazing world which was there, absolutely waiting. A friend of mine came to see me and said that he had the big project, millions of dollars to spend to solve a noise in telephone channels. Something very, very big at that time. So IBM put this group on it, and the man in the group was a friend of mine. He was told to solve it, but not given any idea how to solve it. He said, if you can unscramble complexity of the stock market, you'll be able to unscramble the noise, which must be simpler. And I did. Sometimes declaring a problem impossible is also a great advance. And then wrote a little book. It was in French, actually, and it had no title, because in a certain sense, I had not felt the need of a word for fractal. And the publisher told me, ridiculous, you must invent a word if you wish for that. I thought and thought and thought, went to my son's study room, and he had Latin dictionary, and I started looking for a word which somehow fitted the idea of something I was doing. It was fractal. Giving a word gave the topic a certain reality. It's now in every dictionary. People either think in formulas or think in pictures, and thinking in pictures only in science doesn't take you very far. I was thinking in both, but I was very surprised when in my work I found so many pictures, because they're useful and important, I thought, and people liked because they felt they were beautiful. One of my best-known pieces of work called the Mandelbrot Set. It's a set which the formula is so short that people would think it's ridiculous. It's almost as simple as the formula of a circle. Formula can be very simple and create a universe of bottomless complexity. Amazing wealth of detail which is present there. It's just wonderful.
You can see the beauty of the Mandelbrot set and its really nice fractal feature where you can zoom in until to the interesting things. What I want to talk about is what is this object and what is the picture of. Why do we care about this picture, and why do Mandelbrot set become a Mandelbrot set? The first thing we need to understand is that this entire thing is happening in the world of complex numbers. If you remember complex numbers in the complex plane, it has two axes. With the numbers of the form a plus bi, for example, we plot this one where a and b is real number and I squared is a symbol which is equal to -1 or an imaginary number. And the distance is called the magnitude of a complex number. We may use this in addition, subtraction, and some operations used in complex numbers. So how do we get to Mandelbrot set from here? With complex number c and with the input and output fc of z is equal to z squared plus c, and with the behavior of 0 under iteration of fc, we can see how Mandelbrot set explained through this function from Julia set. For example, from the function f1 of z is equal to z squared plus c, and when we replace the value of z with 0, it will become 0 squared plus 1, which is equal to 1, then 1 squared plus 1 is equal to 2, 2 squared plus 1 is equal to 5, then 5 squared plus 1 is equal to 26, and so on. It is the behavior of 0 under iteration for particular value of c. However, there are two options for this function. 1. Distance from 0 of the sequence gets arbitrarily large, and it is the case 1, means it blows up or not stable. 2. Distance is bounded, or which means never larger than 2, and it is the case 2, which stays small or stable. The Mandelbrot set is the set of complex number c which case 2 hold.
You can see their size is growing, and in particular, we've got some things that are further from 0 than 2 is. Applying this function, well, f minus 1 of 0, that's 0 minus 1, which is minus 1. If we plug in minus 1 to that function, we have minus 1 squared, which is 1, which is 0. Oh, wait, okay, but we know what happens to 0, right? It goes back to minus 1. So these iterates just alternate between minus 1 and 0. And I start iterating 0 under that function, everything remains bounded.
It's the guy.
And this is also, in case you're curious, how these pictures are always generated. So if you want to figure out to draw a picture whether C is in the Mandelbrot set or not, well, you just start iterating 0 under z squared plus c. 0. So no matter how many times we apply the function, we just stay at 0.
So you're in the club.
So you're in the club, that's right. But if we take, like, say, some small number here, it's a little hard to compute without taking a real number, so I apologize. But if we take something like, 1 over 8, something like that. If we start iterating, so the first iterate is 1/8, and then you start adding things under iteration, but it's never enough to get you outside of that disk of radius 2.
These guys are blowing up.
That's right.
These ones are not blowing up.
That's right.
What's happening at the edges then? Is that where things are interesting?
That's where things are interesting, right? Where you go from blowing up to not blowing up